another problem session for the prep. So today we have an interesting problem. So here is a table. Let me get another ink too. Okay, so here is a table. This is supposed to be a frictionless table. So frictionless table. On that is a block, a mass M2. On that is another block, but this one is not frictionless. This surface can be, if it's static, is mu s, mu k values, and between M1 and M2. Okay, so this block and this block can have friction, and it says slides. So there is an instant t problem about instant t when it is sliding on M2. M2 may also be sliding, but because of frictionless, we don't care what's happening as far as friction is concerned here. So because this sliding, this is the friction value that will be important, not the static one. This is static one. If it was not sliding, we'll use the static one, but sliding, so it's going to be kinetic friction. So this thing is connected with a string over a pulley which can rotate, but it is massless and frictionless pulley. And this pulley, this axle is being pulled at a constant acceleration, not constant speed. That will be another problem, but it's going at a constant acceleration. Okay. And so the question is, what are the tension here? What's the tension here? And of course, this muscle pulley, so tension this side will be same as tension this side. So we don't have to use two different symbols. So this is the same. So the question is finding the tension, and tension is same because of massless and frictionless pulleys, right? We've talked about this. If you don't understand this, you should go to some previous videos, and I've talked about is this is the massless and frictionless over here, that makes the tension on both sides must be same. Okay. So you can go ahead and pause this video and try to solve this problem, come back to it. It's a pretty good problem actually in quite different ways. So you may think like, okay, I would just look at from the perspective of I can have a coordinate system so that we can locate this guy and this guy with respect to the pulley. That will work, but that will be accelerating with respect to the table. So that will be a non-inertial frame. So this will be, if I do it like that, if I do that, I'd call this X and Y, and its origin is fixed to the axle of the pulley, then let's call it primes here. So that will be O prime, X prime, Y prime. It's a good coordinate system, and maybe you should try to do it that way. I would not do it. So this will be a non-inertial frame. And for this, whether you write equation for this guy or equation for this guy, so say I'm going to write equation for M1. For M1, it look like a M1 acceleration prime equal to all the F on 1 minus MA, and M2 will look like M2, so A1, A2 prime vector, all the force on 2 plus minus So we need to make a little correction if you do it this way, okay? However, we're going to do it in inertial frame. So we are going to redraw this thing. We're going to redraw, the frame will be here at this point. Okay. And the pulley is over here. So let's call it from, so pulley's location, let's call this big X, and let's call this part is X2, X1. So the front of this is, so from here to here is X1, from here to here is X2, and from here to here is capital X. This is inertial frame. Now here the equations will be M1 A1 equals to F, M2 A2 equals to F on 1, F on 2. That's the equation of motion. They may not be independent because this is string that relates them, and we have X is acceleration of this thing, acceleration is A along the X direction. So this A is basically the second derivative of this guy. So this is an instant t. So d square big X dt squares. So that's what that is. That's the relation between them. It's because that if I can relate these guys with X, then there will be relation between them. One way to look at the relation is say this side of the string will be X minus X1. This side of the string will be X minus X2. And we can ignore this, but you can say this side of the string is, let's see, B. Let's call it this is B. Doesn't matter, but it will not work out. We don't need to know that. All we need to know is that this plus B, X minus X1 plus X minus X2 plus B is the total length of the string. Now if you take a time derivative, this will be 2x minus x1 minus x2 equals L minus B. Take time derivative, then the 2 times the velocity of the pulley at any time. So this is all happening at instant t. Always keep in mind b1x minus b2x, and this side will be 0 because that's constant. And this just says 2 times acceleration plus a1x minus a1x minus a2x equal to 0. So a1x plus a2x equals 2 times acceleration. So this is what we will call this was constraint, and this also came from constraint, right? So when already over here there is no acceleration on the y side, so this just you already know that a1y will be 0 and a2y equal to 0. So those are already known. And X guys are related this way. Okay, so I'll have to set this up and see where the tension fall in. All right, so when I'm looking at this, let's look at the bottom one. Oh, why not just top one? Okay, let's look at this first top one. What the force is on this thing. So this is my M1 and this is M2, right? So force on that will come from over here and over here and gravity. So because it's pushing down, there will be a normal on one will be up, and there will be force on number two. It's okay, just look, let's look at this first, okay, in isolation. So it's from this surface you have a normal from 2, this is M1, so let's call it N, just call it N, and then there's mg, M1g. These are vertical forces, and tension is pulling it that way, and mu k, and this normal with respect to this surface will be the kinetic friction. As a result of all of this, this thing is going as A1 that way. So what do we have? Over the vertical direction, this acceleration here is ax, and around this ay is 0. So this n up minus mg equal to 0, and these are t minus mu k n equals to m1 ax. Of course you can do this from here. You can plug n, and so have a t minus mu k m1 g is m1 a1x. Let's keep calling it a1x, because there will be a2 acceleration 2, right? So this is one. So this is the second equation. So this is equation number 1. Equation number 2, that's going to be useful because we kind of used up this guy already. There's no more use for that. Maybe there's a use for that actually. One, so we can call it 3 and 4 here. Okay. How about this guy? That is the trick part actually. You know, a lot of people can make mistake there. So let's look at that second guy in isolation. See, when you draw something in isolation, you gotta see what surfaces there are. So this is the M2 sitting there. This is the outside body, and then there is this other thing sitting there. And this, so these are the environment of this guy, right? All right. You already know there's going to be mg, m2g, and from this surface there is no horizontal force because no friction there. So all we're going to get from this surface is normal from this surface, but this normal is not the same as that surface. That was surface over there. So this, let's call it m prime. Okay. Now this will be tension, and we're pulling away. Tension is pulling away from that tension. So tension is also in the same direction as that, because over here it also string is that way. So tension is that way. Then there is this surface of contact, and it's the same surface of contact as that guy. So the force is there was that guy in that way, and there's a normal that way. So those are two forces that was associated with that surface, right? So that's the surface, and you have a normal force up on that surface and horizontal force sideways. Now Newton's third law, then I'm going to use Newton's third law. This is actually the reason I'm doing this problem, because it is a very important place where you learn Newton's third law. It's going to be opposite forces will apply on this guy along the same surface. This surface here, this surface, and this surface same. So these two bodies opposite. So this N here is going to go down like that. So there will be force like that. You didn't think of that, right? But there's force like that. And this kinetic friction of this is not only applying on that guy, but also applying on this guy. Mu K N. So these are the forces on this guy, and as a result, it accelerates A to X, and A to Y is 0. Y is that way, X is that way. Okay, so this equation for this guy will look like, along the Y direction is going to be N prime minus N minus M to G equals to M to AY equal to 0. Okay, along the X direction is going to be T plus mu Kn equals to M to AX. All right. This one has an extra unknowns, but we don't need to know that. If there was a friction here also, then we would need to know that. Why not just put that friction also? Okay, let's say this was a friction here, was this friction, kinetic friction is say mu K prime. So mu K prime, the n prime, then you'll have kinetic, if it's whichever is sliding, then there will be also kinetic friction. So maybe let's see at this instance the V is this, we don't know. We're sliding that way, then is mu K n prime will be there in that direction. So there will be minus mu K n prime that way. So this will be the case if it was if you had a friction. So assuming, going back to frictionless table, maybe you should do the friction part also, but I'm not going to do it. I didn't start out like that. So this will be missing, right? So we'll just have this part for frictionless table. So in that case, this N is here also, but we already found the N earlier. It's the same N as this guy, which is M1G. So this one becomes T plus mu K M1G here equals M2 A2X. And we're just wanting to find T. And we have all these equations. Let's put them together. So this is let's call it number 5, or maybe A, B, C, D, and this will be the number 3. So these 3 equations, this one rewriting over there, T plus mu k m1g equals m2 a2x. And I'm supposed to solve for T. Well, the strategy to make you may want to just say, oh, if I add it, these guys go away. Yeah, that's true, they go away. Then you have m1 a1x, m2 a2x. But this guy is a1 plus a2x. So better to make use of that is to get rid of this first. So write this equation in, so that just write a1 on that side. So T over m1 minus mu kg equals a1x, and this one similarly you do T over m2 plus mu k. Now this complicates here. It will not cancel. If I add these guys now, then I can make use of that. Add these guys. So T becomes a common 1 over m1 plus 1 over m2. Make it minus coming on the other side, minus mu k g is common 1 minus m1 over m2 equals sum of these guys equals to 2 times a, and this was given. Of course, it's a matter of simple algebra now. T is equal to 2a mu kg m2 minus m1 over m2 divided by 1 over m1 plus 1 over m2. So that's big phrase expression. This big expression is the answer. All right. Now I've suggested you go back and try to do it. What if there was a table of friction? So if I had done that, I would have gotten over here n prime should have been n1 plus n plus m2g, and n was m1g plus m2g. So n prime will be m1 plus m2g. Kind of makes sense in this problem. So I have a minus mu k m1 plus m2. This equation will be like this, plus t plus mu k m1g equals to m2ax, and so this would have cancelled that, and this would have been t minus mu k m2g equals m2ax, and then I would divide this. T over m2 will be mu kj, a2x. These are a2x. So this would be my, instead of this I would have instead of this I would have this equation, and let's call it 3 prime, and write 2 prime using 2 prime using 2 was t over m1 was using this is mu kg plus a1x from 2 prime. I think that's correct. If you look at bring this on the other side, divide by m1. So now you add these guys become, this will become 2a. So t now is going to be 2a plus 2 mu kg over 1 over m1 plus over m2. I hope I didn't make a mistake in doing algebra. Just wanted to complete our discussion. This is a very good problem. Let me just go back and really emphasize where you should understand. You should understand this part very well, okay? These diagrams very well. So just make sure you understand one more time. So this is the M1 and this is M2. So when you're looking at M1, you have a normal between 1 and 2. Let's call it normal, which I'm calling 1, just n. So when we look at M2, this force is a pair force. So normal force between those two. And if kinetic friction is this way, then the kinetic friction on this M2 will be that way. This is very important to understand. That's why I redid it, okay, because this is on M1, same forces on M2. Hope this helps. You like this kind of clean explanations and problems. You may want to subscribe to this channel. You get reminded, I guess. I don't know and how subscription works. Also tell your friends. Their friends or teacher that this is a resource that you found useful. All right, take care. Bye.